Hi, my name is Ariana, and this is my video lab report for Physics 3212 with Dr. Barron's Lab 5, Magnetic Braking with Faraday. The purpose of this experiment was to observe and model the interactions that occur when a bar magnet is dropped through an aluminum foil tube and compare the results using Faraday's law. The results of the experiment are that the experimental time the magnet took to reach the bottom of the tube was 1.244 seconds, while the computational time was 1.188 seconds. Here are some important background equations such as the Biot-Savart law, Faraday's law, Newton's second and third laws, and Lenz's law. The models for this lab are an experimental model and a computational model, where the system is the bar magnet and aluminum tube, and the surroundings are everything else. We assume the bar magnet is a magnetic dipole to apply the Biot-Savart law, and that the magnetic force from the tube and the gravitational force are the only forces acting on the system. The experiment procedures are as follows. First, use the magnetometer app to determine which end of the bar magnet is north. Next, hold a tube of aluminum vertically and drop the magnet through it. Finally, use your phone to record the magnet dropping and find the exact time of the fall. Repeat these steps for 5 trials to find the average experimental time. The data collected can be seen on the tables to the right. Answering the 2 checkpoint questions, why can't we use a ferrous tube, for example, a steel pipe? We can't use a ferrous tube because it would create an induced magnet that would interfere with the falling magnet. What happens to the magnet? How does this compare to the magnet falling in free space without a tube? In the experiment, the magnet took longer to fall through the tube than through free space. Here are the results of my computational model. The cylinder is the tube, the red is the increasing induced current ahead of the magnet, the blue is the decreasing induced current behind the magnet. The graph is explained better in the later slide, and the computational time was 1.188 seconds. Walking through my glow script code, first I created the functions for magnetic field at any location and the time derivative of flux. In this next portion of the code, I calculated the gravitational force on the magnet. I then used Faraday's law to find each ring's current. Then I calculated the magnetic field at each ring and thus the magnetic force on each ring. I then summed the magnetic force on the magnet from each ring. Finally, I used Newton's second law to find the net force on the magnet and continuously update its position and velocity. I finally plot the velocity over time and print the time that it took for the magnet to exit the tube. Now I'm going to interpret the simulation. Which color corresponds to the clockwise current and which to the counterclockwise? How can you know? The red corresponds to the counterclockwise and the blue corresponds to the clockwise. We know because of Lenz's law. Induced current flows in the direction where magnetic field will oppose the direction of the change in flux. What happens to the dynamics of the system when you flip the magnet around? The induced current will run in opposite direction, but the magnitude of the magnetic field remains. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? The time in real life was 1.244 seconds, and it was longer than the computational model, which was 1.188 seconds. The computational model does not account for external factors such as air resistance or dimension inconsistencies within the tube. Adding these factors into the code or margin of error function may increase accuracy. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? When the magnet is in the tube, the velocity and forces on the magnet are constant, no acceleration. When the magnet is not in the tube, the velocity has a negative slope, so the net force is unbalanced in the negative direction due to gravity. Comparing the experimental and computational model, one can see the experimental time is greater than the computational time. Sources of error include human error for measuring dimensions of the tube, other sources of magnetic field as the experiment was not conducted in an isolated environment, and other external forces such as air resistance that were not accounted for. What if the resistivity of the conductor was reduced to as close as possible to 0? How would the dynamics of the falling magnet change? Well, I equals EMF over R, so the induced current would increase, and therefore the magnetic force on the magnet increases. The magnet would fall slower through the tube. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? Holes or slots would reduce the number of complete rings and result in less aluminum to create an induced current. A decreased induced current decreases magnetic force, and therefore the magnet would fall faster. Thank you.